On this worksheet, we're going to be drawing molecules using three-dimensional or 3D notations, which a lot of times chemists refer to as wedge and dash notation. So in this style of drawing, we imagine the molecules just kind of sitting on your paper, sitting on your desk. And when we draw that molecule, like as it's sitting on your paper or sitting on your desk, we're going to use the traditional straight lines to represent bonds that are sitting flat on the paper. So this would be just the same type of straight line, whether it's a single bond, double bond, triple bond, whatever. The same type of straight lines we would use for a Lewis structure, and so that's used to, I'm going to turn it back to a single bond, used to represent a bond that is, I'm going to say it is parallel to the paper. Referring to like whatever paper you might be working on. And I realize that kind of looks like a number one, so I'm just going to sort of angle it so that it doesn't look like a number one. So a straight line bond is used to represent a bond that is parallel to the paper, parallel to the desk, laying flat. And any bonds that are sticking up out of the paper, we draw them in what we call a wedge format. So this would be a bond that is sticking up. If you imagine this molecule sitting on your paper, this bond is going to be sticking up at you. And then we also want to think about the potential that bonds would be sticking down. So this would be basically like they're embedded down into the paper. And for that, we use what we refer to as a dash. So this dash notation is when the bond is pointing or sticking down. And in this situation, that would be referring to sticking down into the paper. So for these like 8 molecules, I think we're going to use this wedge and dash notation to represent these molecules in 3 dimensions. Really easy if you have a model kit and you can build the models. That's going to help a lot. And since I can't use a model kit on something like this, I'm going to use this website called moleview.org. This website allows us to come up with like models or representations of these different molecules. So the first one we're going to do is nitrite NO2 minus, and I'm just going to Google that, nitrite ion. I'm going to pick the one that says it has a -1 charge, and I want to be viewing this 3-dimensionally, so I'm just going to kind of change the perspective here. Yeah. So here's a 3-dimensional picture of the nitrite. It is a nitrogen in the center that's represented by the blue, and then the 2 red spheres are the oxygen atoms, and then we've got the double bond and the single bond, and the software allows me to just sort of rotate it so we can see what it looks like in 3 dimensions. There's also a lone pair of electrons on the nitrogen, which is not being represented by this software. That's one of the disadvantages of this software. To draw this 3-dimensionally, or draw any molecule 3-dimensionally, the easiest way to do it is to put as many atoms as possible flat with the paper. So if I angle the molecule this way, you can see that the nitrogen and the oxygen atoms are all like in the same plane. They're all parallel to each other. And what I'm going to do is angle it so that they are all sitting flat on the surface, sitting flat on the screen or flat on the paper like that. And we're just going to draw what we see. Remember, the blue represents the nitrogen. The way that we're looking at it right now, we've got a single bond to the oxygen to the left and a double bond to the oxygens to the right. And then remember, I told you there is a lone pair of electrons on that nitrogen. We just can't see that in MolView. There's also lone pairs of electrons on the oxygen atoms as well. For the 3-dimensional drawings, we don't need to worry about brackets with the charges, but you could if you want to. Now, this question is asking us also to classify this molecule as being polar or nonpolar. And one of the really easy things that you can do for classification, when we're trying to decide if a molecule is polar or nonpolar, the very first thing you should always do is look at the central atom and ask yourself if you have any lone pairs on the central atom. If you only have 1 lone pair of electrons on the central atom, then you are looking at a polar molecule. Polar molecules are ones that have uneven distribution of electrons around the atom or around the molecule, and sometimes that can be a really difficult thing to determine. But if you have that 1 lone pair of electrons on the central atom and it's not being balanced by a lone pair of electrons on the other side of the atom, which is going to be impossible if there's only 1 lone pair, so that's always going to make the molecule polar. Let's take a look at the second one we're going to work on, NCl3. Again, I'm just going to search for this. This would be nitrogen trichloride. You can also build these molecules in MolView, but it's easier to be able to look them up if you can. So this, the green are the chlorine atoms and the blue is the nitrogen. And as I rotate this around, one of the things that hopefully you notice is that the nitrogen and the chlorines are not all in the same plane like we saw with the NO2. So the oxygen, or the nitrogen, I mean, if I rotate it like this, the nitrogen atom is raised up, like it's kind of buckled up a little bit higher than the chlorines. There's also a lone pair of electrons on that nitrogen as well. So for drawing this, what we want to do, like I said, is put as many atoms as possible in the plane of the paper. We also always want to have our central atom in the plane of the paper. So that's going to be our nitrogen in the center. And let's look at it so this chlorine, I keep forgetting what's what. The green chlorine that's at the top right now, as we look at it, that chlorine is flat with the paper. And the chlorine that is angled down to the right, that one is flat with the paper as well. And then hopefully you can see the chlorine that is on the left-hand side, that one is actually sticking up at us. So the way that we would want to draw that is just going to look like this. That chlorine that's sticking out at us, that's going to be on what we say a wedge bond because it's sticking out at us. Don't forget that we also have a lone pair of electrons on the central atom, which means that the molecule is polar. There are also lone pairs of electrons on the chlorines as well. If you're getting a little bit confused about are the lone pairs there or are they not there, if you start with a Lewis structure first, the Lewis structure is going to show you the location of all the lone pairs. And then once you've got the Lewis structure drawn, you can convert it to the 3D drawing and you can keep those lone pairs with you in the conversion process. Let's do water next. Here's the water molecule, and there are, on the oxygen atom, which is red, there are 2 lone pairs of electrons. Like the first molecule that we looked at, these 3 atoms are all parallel to each other. They're all in the same plane. So this is one that's easy to draw. We'll put that oxygen in the center, stick the hydrogens like that. And then we've got 2 lone pairs on the oxygen atom. So what do we do when there's 2 lone pairs? It's kind of tricky to visualize this in MolView because we can't see the lone pairs in MolView. So what I'm going to do is switch to a different molecule. So instead of water, I'm going to do carbon. No, I'm going to do dichloromethane. Dichloromethane is not the same molecule as water, but we're going to pretend like it is. And in this representation, what we're going to do is pretend like the gray circle in the center, that's our oxygen, and the green spheres, those represent our hydrogen atoms, and those 2 white spheres up at the top, those are going to represent our lone pairs. So I'm going to kind of hold it like this so that it sort of matches up what we're looking at with the way that I've drawn it on the left-hand side. So we want to be thinking about those lone pairs of electrons. How are they, sort of distributing the electrons around the molecule? Again, polarity has to do with how evenly or unevenly the electrons are distributed around in a molecule, and we're really focusing a lot on lone pairs that are on the central atom. So when we're looking at the lone pairs on the central atom, we want to ask ourselves questions like, how balanced are they? Do they balance each other out? When there's only 1 lone pair on the central atom, it's not being balanced out by anything, which means that the molecule is going to be polar. When you have 2 lone pairs in the central atom, you have to think about how well do they balance or counteract each other. And this is really a dimensional thing. If those 2 lone pairs are exactly 180 degrees apart, if they were exactly opposite from each other, one would be kind of pulling to the left and one would be pulling exactly to the right, they would sort of cancel each out like a game of tug of war. But in this case, the lone pairs are not exactly opposite. They're both angling up, one to the left, one to the right, which means that they're not canceling each other out. And this molecule is also polar. They can only cancel each other out if they are exactly opposing each other on that central atom. And since in this molecule, they're not exactly opposing each other, they're sort of at an angle, not exactly opposing each other, that means that the molecule is still polar. It's a pretty tricky concept. Let's take a look at our next example, SF4. Now, if I remember correctly, MolView is like programmed wrong and it actually messes this drawing up. So I'm going to actually pull up the drawing of something different. I'm going to pull up phosphorus pentachlor. I think I can pull up phosphorus pentachloride. Yeah. So MolView, like I said, is programmed incorrectly for the shape of SF4, so I'm not going to actually pull it up because it'll give us a completely wrong structure. This is also not the structure of SF4. We're going to have to imagine from this. But this is sort of what it looks like. In this particular structure, we have these 3 green spheres that are on the outside perimeter, the way we're looking at it right now, that they make up kind of a triangle shape. And typically we draw those 3 green spheres, whatever they might be, in the sort of the center. We call it the equator or the equatorial position of the molecule. And then in addition to those 3 green spheres, we have 2 green spheres. Now the way I'm holding it, they are, trying to get this rotated, they are kind of 180 degrees apart from each other. They are in a line. So we're looking at the green sphere that's on the left versus the green sphere on the right. And if I rotate it, you can see that they're in a line with that orange sphere in the center. So this is the SF4 molecule, the general shape. The orange in the center is going to be the sulfur, and then the green spheres are going to be the phosphorus. The model has 5 green spheres, and our molecule only has 4 instead of 5. So what we want to visualize, what we want to imagine is that one of those green spheres is a lone pair of electrons instead of an atom. And what we're going to do, the way we're looking at the molecule right now, the green sphere that's on the very right-hand side in the equator, that's the one that we're going to imagine is our lone pair. So the orange is the sulfur in the center, and we have 1 phosphorus that's sticking straight up and 1 phosphorus that's sticking straight down, and I've decided to put the lone pair on the sulfur over there on the right-hand side. And then we have these 2 phosphorus atoms that are on the left, and as I kind of tweak this rotation a little bit, hopefully you can see that one of those phosphorus atoms on the left-hand side is sticking towards us, and the other phosphorus atom is sticking away from us, which we use with wedge. We represent that with the wedge and dash notation. Is this molecule polar or not? To answer that question, we focus on the central atom. There is only 1 lone pair on the central atom, which means that we do not have evenly distributed electron density. It's impossible when you only have 1 lone pair, so this molecule is polar. Next, we have IF3-, that is iodine trifluoride. And here is what that molecule looks like. If I angle this just right, you can see that all 4 of these atoms are all in the same plane. We could draw it, let's draw it like this from this perspective. The purple is the iodine. We have fluorines sticking up and down and to the left, lone pairs on all of those fluorines, and 2 lone pairs on the central atom as well. To imagine whether this molecule is polar or not, we probably want to go back to the structure or the model of phosphorus pentachloride. Phosphorus pentachloride. And in this representation, we want to imagine, so the way I'm holding it right now, those 2 green spheres on the right-hand side, those are going to be our lone pairs. The 2 green spheres on the right side will be our lone pair. So what we want to do is look at the relative position of those 2 green spheres. If those 2 green spheres are perfectly opposite each other from that central orange atom, then the molecule will be nonpolar because those electrons are balancing each other out. But if those 2 green spheres, our lone pairs of electrons, are slightly angled with respect to the central atom, it will be polar. So as I twist this molecule, again, remember we're focusing on the green spheres on the right-hand side. As I twist it, we can see from this perspective, they're about 120 degrees apart. They're not perfectly opposite from each other. That makes this molecule polar. And now we have I3 minus. So I'm actually just going to leave it on this structure right here. I3 minus is going to look really similar to this molecule. I'm going to try to hold it in a way that lets us imagine. There are 3 iodine atoms, and they are all connected in a straight row. So the way that we're looking at the molecule right now, you could imagine the green sphere on top, the orange sphere, and the green sphere on the bottom. Those are the 3 iodine atoms in this molecule. They're all linear to each other. So if I twist it, you can see that they're all lined up. There are 3 lone pairs on the central iodine atom, and they are in the position of the 3 green spheres that are all along the equator of this particular molecule. So as I'm rotating it right now. Now we have to decide if this molecule is polar or nonpolar, and to do that, we're going to look at the relative position of the lone pairs on the iodine. So the examples that we've seen so far, we've had ones that have had 1 lone pair, and that's always polar because there's no even distribution. And we've looked at ones that had 2 lone pairs, and I've said if those 2 lone pairs are perfectly opposite from each other, the molecule will be nonpolar because the lone pairs balance. If the lone pairs are not perfectly opposite from each other, like if they're at an angle, the molecule will be polar because they don't balance. Now we're looking at a molecule that has 3 lone pairs, not 1, not 2, and I'm going to turn it like this so that we can see those 3 lone pairs. The 3 lone pairs are now the green spheres that are at the top, the bottom left, and the bottom right. So we have our central iodine, and we have a lone pair, and a lone pair. And look at how, because there's 3, even though they're at an angle, each one is 120 degrees apart, they are perfectly arranged and perfectly balanced with respect to each other, which makes this a nonpolar molecule because of that perfect symmetry and distribution of the lone pairs. All right, we've got 2 more to go. We have XEF5. Let me see if I can find it by its formula. XEF5. Ooh, that's not what I was looking for. XEF5 plus. Maybe not. We'll try Xenon, penta, fluoride. Before making this video, I looked all of them up except for the last 2 because I had such good luck with all the rest of them. Let's kind of skip it for now and let's see if we can find that xenon tetrachloride. Xenon tetrachloride, close enough. So we'll go with XeCl4. We'll call this XeCl4, even though it's fluorines instead of chlorines. They bond the same way. So there's this molecule right here. This is what it looks like. As I turn it around, you'll see that all of those atoms are in the same plane. So they're all flat with respect to each other. Let's think of an easy way to draw this. Remember, it's been a while since I said this. The easiest way to draw these molecules is if you put as many atoms as possible in the same plane, and that being the plane of the paper. So if we just hold this molecule flat like this, that blue is the xenon in the center, and then we've got our chlorines, top, bottom, left, and right. We do have in this molecule 2 lone pairs on the xenon, so we'll just kind of fit them in wherever we can on this drawing. Plus, we also have lone pairs on the chlorines as well. So we want to think about, is this molecule polar or nonpolar? And that's going to have to do with the relative position of these 2 lone pairs on the xenon. So to visualize this, I'm going to switch to a different type of a molecule. Let's do sulfur hexafluoride. Sulfur hexafluoride is going to give us an opportunity to visualize. And what we want to do in this case, so as I'm kind of angling it right now, we've got that yellow in the center. That's going to represent the xenon. We've got those 4 green spheres that are all in our equator, and those will represent the chlorines. We have 1 green sphere on top and 1 green sphere on bottom, and those will represent our lone pairs. And if you look at these green spheres, the one on the top and the one on the bottom, I'm going to flip it. you'll see that those two green spheres are exactly opposite from each other. They are perfectly 180 degrees apart. One's on this side, one's on that side. They're perfectly balanced, which makes that molecule nonpolar. So with this, let's go back to the one that I skipped, XeF5+. Now that molecule has the same shape as what we're looking at right now, except for one of those green spheres is going to be replaced with a lone pair. So the yellow in the middle is going to represent the xenon, and we're going to have 4 fluorine atoms. We'll say those 4 atoms that are in the equator, those are going to be the fluorine atoms in the molecule. Notice that to the left side there are there's 1 fluorine sticking in front, and in the left side 1 fluorine sticking back. Same with the right side. 1 is sticking to the front and 1 is sticking back. Lone pairs on those guys. And then we've got two more spheres in the model. We have 1 more fluorine in the actual molecule. Let's say that the fluorine that's up on the top, or the atom up top, that's our last fluorine, that's our 5th fluorine. And the sphere that's down at the bottom of the molecule, that is a lone pair on the central atom. Is XeF5+ polar or nonpolar? It is polar. Again, that is because there's only 1 lone pair on that central atom.